everybody. Good to see you today. I just want to remind you before we start our lesson of your to-do list that's on the whiteboard. Make sure all of these things are done so you're ready to go for our lesson, okay? Okay. So I have a couple of items today that I want to share with you. So what is this? What do you notice about this apple? Katie?
It's cut.
It's cut, but what happens when we cut an apple? That's right. It browns a little bit. What do you think causes the browning?
Oxidization.
Oxidation. You're ahead of the game. Yes, oxidation. And now, what is this? I don't know if you can see.
A nail.
It's a nail, but there's something on it. Class, can take a look. Take a closer look. What's on it?
Rust.
Rust, yes. And what is rust? What do you think causes rust?
Oxidation.
Oxidation,
Yep.
yes. Just remember to raise your hand
Yes,
before
ma'am.
you speak. Yes, so what would both of these processes be? A chemical or physical change? Katie?
Chemical change.
Chemical change, correct, because a new substance was formed. The old substance was broken down and a new one formed. So in the case of this iron nail, it would be iron oxide was formed. So yes, a chemical change took place. So in today's lesson, you're going to determine whether a reaction is redox or not. And you're also going to be given the oxidation states of the reactions. In past lessons, we categorized different types of chemical reactions, and redox was one of them. And in the future, we're going to also be working with redox equations where you will have to figure out the oxidation states on your own. But today, I'm going to give you the oxidation states because the main thing about today's lesson is I want you to be able to recognize whether an equation or a chemical reaction is oxidation reduction or not, and whether it's in a living system or a non-living system. So what would you say about the apple? Is that a living system or non-living system? Katie?
A living system.
It is a living system, yes, because those apple cells are living until they're cut. What about the nail? Yes, Katie?
Non-living system.
Yes, it would represent a non-living system. So after this lesson, when you're given a chemical reaction and the oxidation states of each element involved in a living or a non-living system, you will be able to distinguish whether the reaction is oxidation reduction or a non-redox reaction, and in a living or non-living system, hopefully with 80% accuracy. That's the objective for today. Okay? So let's talk about chemical reactions and chemical changes in substances. So how do we model what happens in a chemical reaction? What is that called? How do we represent what is happening in a chemical reaction? So Jeremy, what about you? Do you know? Not quite sure? Okay. All right, well, we're going to talk about it. What about the past lessons we had about recognizing and categorizing the types of chemical reactions? What did we look at to determine that? Okay, so we looked at chemical equations. Remember that the reactants are on the left side of the equation, the products are on the right side of the equation. Okay, so we know that a chemical reaction has taken place when the reactants on the left side change into something different on the right side. And we'll look at some equations in a little bit. Okay, so we're going to get into our new material, which is about redox equations in living and non-living systems, okay? So you're going to remember, you're going to take notes. Everyone should be taking notes or looking at their pre-printed notes if that's your situation, and participating. I expect participation from all students, okay? And if you have a question, please don't hesitate to ask. So pre-printed notes. Okay, so I'm going to write some facts about redox equations on the whiteboard. Okay, so what is a redox reaction? Let's think about it. When the nail rusts, when the apple browns, when other fruits brown, what's actually happening? Chloe? Yes, oxygen is hitting the surface. That's not always the case, and that is a very good answer. But we're going to go into more detail about what happens, okay? So what is actually happening is that energy is transferred between substances through the transfer of electrons. So let's write that down. Energy is transferred between substances. I'm going to abbreviate that. Through the transfer of electrons. And then I'm going to write electrons with an E and a negative sign, which you can do also. That means electrons, okay? Okay, so in these reactions, these chemical reactions, we have electron transfer. So that's one of the facts about redox reactions, okay? So what is required for a reaction to be considered redox? What is required? If we're transferring that electrons, then what must be happening to one or two of those reactants? Katie?
It needs to be exposed to oxygen.
Not always exposed to oxygen, but sometimes, yes, sometimes. The main thing I'm looking for is that the substance in a reaction will either gain or lose an electron. So if a reactant loses an electron, that means one of the other reactants gains an electron. Okay, so let's write that down. Substances either lose or gain an electron. So like we said, I also want you to write down, not all redox equations contain oxygen or hydrogen or involve oxygen or hydrogen. We learned how to recognize redox equations or reactions that way when we were classifying different types of chemical reactions. But today we're going to talk about not only those types, but other types as well. So they don't all require oxygen is O2 or hydrogen H2. So if they don't all contain oxygen or hydrogen or involve oxygen or hydrogen, what do you think is involved? Katie?
Some form of chemical reaction.
Yes, there's definitely a form of a chemical reaction involved. What are the different types of elements that we have in the periodic table? What are the classifications of elements? We have noble gases, we have earth metals, we have metals, right? Transition metals. So one of the other areas of redox involve the electron transfer between two metals, okay? So we're going to write down transfer of electrons between two metals. Okay. So one example of this would be, do you guys remember galvanic or electrochemical cells that involve the zinc and the copper anode and cathode? So anyway, that is an example of electron transfer between two metals, because you have the zinc and the copper one's in the anode, one's in the cathode, and they transfer electrons and transfer energy via those electrons. Okay, so now we're going to watch a short video we're going to talk a little bit about redox equations. I hope you find it funny. I thought it was pretty...
Who wants it, and what they're willing to do to get it. Electrons are what make it possible for an atom to bond with other atoms to form molecules, and when that happens, a tremendous amount of energy can be exchanged in the process. But not all chemical reactions involve electrons changing hands. Acid-base reactions, you'll recall, are more about swapping protons. But because electrons are a real point of the realm in chemistry, the most important reactions that take place on Earth involve the transfer of one or more electrons from one atom to another. These are redox reactions. Redox, which is a portmanteau of reduction, oxidation. But what's up with those words? We know what reduction is, making less of something, and then oxidation maybe has something to do with oxygen, well, sometimes, but not always. These are actually super terrible choices for what is actually happening in redox reactions, but we are stuck with them. Reduction is when a substance gains electrons. Yes, it gains, which is the opposite of what the word reduce means. Fantastic. And yes, sometimes I want to punish the people who named these things so inaccurately, but they didn't know any better and they're all dead, so we can't do anything about it. Protochemists would make pure metals by heating or smelting their ores. And they noticed during the smelting that these substances would become lighter. So I guess it's not crazy that they decided to say that these substances were being reduced. Our old French friend Antoine Lavoisier figured out that this was because oxygen gas was actually leaving the compound, making it lighter. What he didn't know was the actual chemistry involved. Oxygen is, unsurprisingly, the quintessential oxidizer. It pulls electrons off of one molecule to make itself more stable. But if you heat it up enough, it gets all energetic. Today, we understand that oxidation and reduction are all about electron transfer. So you might think that we renamed them, and some chemists have tried producing terms like electronation and de-electronation. But once a set of terms is decided upon and used for a while, it's pretty difficult to uncreate it. So we're stuck. To keep these seemingly nonsensical names straight, I rely on the phrase oil rig. Oxidation is loss of electrons, reduction is gain of electrons. We just gotta know
Write
this
that
stuff.
down.
Because
We're
it's
going to
a-
be writing it
Your
later.
cells
Go ahead
convert
and
sugar
write it
into
down.
energy so you can move and breathe and think. That's redox. When plants photosynthesize sunlight into food, that's redox. The battery powering your laptop, redox. Fire, also redox. Since electron swapping is the name of the game here, when you study redox reactions, it's important, critical, absolutely essential to keep track of the electrons. Think of them as dollars or pesos or pounds or euros. In any transaction, one person is going to gain them and the other is going to lose them. And to stay on top of things, you have to keep tabs on who's ahead and who's behind. Atoms are fond of sharing electrons, though, forming covalent bonds, so sometimes keeping track of where they are and where they're going to end up isn't quite so simple. Let's think of every covalent compound like a marriage, though it's going to be...
Okay. So I'm going to stop it there because that's basically what you need to know today. So let me get this down. Okay. So what was the main point? So we know that redox reactions involve transfer of electrons, right? So can anyone tell me what they learned about the transfer of electrons? What are the two main words in redox? Katie?
Reduction and oxidation.
Right.
Oxide.
Oxidation
Yeah.
and reduction, yes. So can you tell me what is, and write this down if you didn't already write it down from the video. So can anyone tell me what is oxidation based on what you learned so far from the video? Katie?
A substance that loses electrons.
Okay, so oxidation we can define as the loss of electrons. So write that down, equals loss of electrons. Okay, what about reduction? Katie?
When a substance gains electrons.
So if oxidation is the loss of electrons, then reduction is the opposite of what it sounds. The reduction is the gain of electrons. So that's what can make learning these terms a little confusing is the terminology, because you would think that reduction would be losing electrons, but it's actually the gain of electrons. So how do we remember that? How can we remember that? Any clues? Anyone have any ideas? Yes, Katie?
Well, something that I kind of put together in my head is with reduction, it could be reducing from something else. Like,
Right. It can be, yes, reduced from something else. What was the acronym that they mentioned in the video? Did anyone write that down? Jeremy, did you write that down? No? Okay, well, we're going to write it down right now. So this is a good way to remember oxidation and reduction and what each one means. So we have the acronym oil, and then Rig. I'm going to write it over here. You can write it down your paper if you want. I'm just running out of space. Okay, so what do you think the O stands for in oil? Katie?
oxidation.
Oxidation is loss. Okay, so that's one way that we can remember what it means. Oxidation is loss, and we have the acronym OIL. And then what about reduction? Sorry, I just gave you the answer. So RIG, the R in RIG is reduction. And reduction is gain. I tell you, I wish I had this acronym when I was learning chemistry because it really helps. So that's your acronym for remembering oxidation and reduction and as far as transfer of electrons go. Okay, so we have this information now. So how do we tell when we look at a reaction? Can we just tell by looking at it if oxidation and reduction took place? Chloe? Right, no, we can't. We can't just look at it. We have to investigate just a little bit. And how do we investigate? What do we look at? Does anyone remember what the oxidation state means? We had this a little further back in some lessons further back. Remember I mentioned the oxidation state earlier in the lesson, and I told you I was going to give you the oxidation state today. right, so no one remembers? So the oxidation state is the charge that an element has at the time. So some elements have more than one oxidation state. So we're going to look at a reaction, and I'm going to give you each of the elements' oxidation states. So what do you think happens to the oxidation state in a redox reaction? So say we have reactants A and B. So those are the reactants. And then we get products A, B. So what do you think is going to change if it's a redox? Katie?
Either A or B is going to lose electrons.
Good, yes. So A or B they're going to transfer electrons. So what does that mean about their oxidation state? So say that A has a +2 oxidation state and B has a 0 oxidation state. And then in the products, B will have a -2 and A will have a +4. Yes.
B lost electrons and A gained.
Okay, look at it again. So if it has a positive charge, that means it lost electrons. And if it has a negative charge, that means it gained electrons. So that means that the oxidation states are different. So that means this was a redox reaction. Okay, so just remember, when an element becomes more negative, so we're going to say oxidation, here's another way to remember it, equals increase in positivity, okay, of the oxidation number. And reduction equals an increase in negativity. So that's another way to remember that, okay? Okay, so I'm going to go on to, let's do some guided practice on determining whether a redox reaction is occurring, number one. Is it occurring in a living or non-living system, number two. And that's it. So is it occurring, and is it occurring in a living and non-living system, or non-living system? There we go. Okay. All right. So here are some. I want you to take notes. Everyone needs to participate and take notes on this because you're going to need this for your research. Okay. So redox. Some examples of redox reactions in living systems are glycolysis, which is the breakdown of glucose in the body, photosynthesis, which is when plants react with carbon dioxide and change it into oxygen so we can breathe. Cellular respiration is when we emit carbon dioxide, and the browning of fruits, which all involve different chemicals and processes, but one of the common things is when they're exposed to oxygen. Okay, so let's look at, oh, you want me to go back? Okay. Any questions about redox reactions in living systems? Okay. Okay, some redox reactions in non-living systems. Remember we had the rusty nail, the oxidation of metals. Another reaction that's redox in a non-living system is the combustion of fuel outside of living things. I mean, we have like glycolysis is also the combustion reaction of fuel inside our bodies, but it doesn't catch fire. So the burning of fuel outside of living things, such as petroleum, wood burning, and other things. These are examples of combustion reactions, which are also redox reactions. And then, as we said earlier, with the galvanic cell or the electrochemical cell, this is electron transfer in batteries. Just hold your pencil up when you're done copying down these notes. Okay. All right. Let's move on. So now let's look at the chemical reaction for redox equation, or the chemical equation for redox reaction. Sorry. So we see that we have iron, the metal iron, which any element in its natural form or has a charge of 0. So elemental oxygen, which is in a diatomic element, it is in its oxidation state is 0. Okay, so look what happens to each of these oxidation states when rust is formed. When iron 3 oxide is formed, what happens to those oxidation states? Jeremy? Yes, one becomes positive and one becomes negative, which signifies that electrons were transferred. So yes, an oxidation reduction reaction took place. Okay, so now we can use our acronym OIL. Oxidation is losing. Which one loses? Iron. And RIG, reduction, is gaining. So which one is gaining? Which element is gaining? Katie?
I'm sorry. My brain.
It's okay, go ahead. Which one is gaining electrons? Yes.
Oxygen.
Oxygen, right. And how do we know that?
The negative sign.
Because it's increasing in negativity. Yes. So it's gaining electrons. Okay, so would the formation of iron oxide be in a living or non-living system? Katie?
Non-living.
Non-living, right. Okay. So the reaction is redox because iron loses electrons and oxygen gains electrons. So, and that is why rust on a nail is the product of a redox reaction. Because a new substance is being formed because The iron loses electrons and the oxygen gains electrons. Okay? So this reaction is the oxidation of iron or formation of rust. As you can see, these nails have rust all over them. The exposure of the metal to oxygen in the atmosphere takes away from the metal and forms another compound called iron oxide or rust. Okay, another example of a redox reaction is glucose and oxygen react to form carbon dioxide, water, and energy. Okay, so let's look at the oxidation states of each of these elements. Do they change? Well, it's kind of hard to tell because it's broken apart. So it forms just different products. So this sugar is broken down into carbon dioxide and water. So it's kind of hard to keep track of the oxidation numbers, but you can see that the carbon has changed to +4. The hydrogen is the same. The oxygen, actually this oxygen has changed to from 0 to -2. So has a redox reaction taken place? Chloe? Yes it has, very good. So we can use oil rig again, and we can see that oxidation is losing, so the glucose is being oxidized, and the oxygen is being reduced. Is this in a living or non-living system, Katie?
Living system.
Living system, right. And what do you think this represents?
The transition that glucose goes through when it's in your body into energy.
Yes, it's transforming, it's glycolysis, it's transforming glucose into energy that we can use. Okay, so glycolysis is part of cellular respiration. So that process is called cellular respiration, and it occurs in living systems. Cellular respiration is how food is converted to energy we can use. So this is a redox reaction because the glucose loses electrons and the oxygen gains electrons to produce water and energy. Okay, so here we have a combustion reaction. So we have methane is exposed to oxygen and heat, and it produces carbon dioxide and water. So is this reaction redox? Jeremy? Okay, well, let's look at the oxidation states. Do the oxidation states change? Let's look at carbon. Yes, the carbon has a -4 oxidation state, and it changes to +4. So it loses electrons. So yes, we can say that this was a redox reaction. And is this burning of methane fuel in a living system or non-living system? Katie?
Living system.
Well, this is a combustion reaction of a fuel, like yes. So it would be in a
Non-living system.
right. Very good, non-living system. So this is like a fuel like butane. Methane is a fuel like butane. Or propane. So they're all related. So carbon loses electrons and oxygen gains electrons. This is a combustion reaction and is in a non-living system. This reaction is the combustion of methane gas. Okay, so what about this one? We have the sodium hydroxide and hydrochloric acid to form sodium chloride salt and water. So let's examine. So what is NaOH? Yes, Katie?
Sodium hydroxide.
It's sodium hydroxide, but what is it classified as?
A metal.
It's Good try, but it's, so what is hydrochloric? Well, it's in its name.
Yeah.
Hydrochloric acid is an acid, so what do you think that sodium hydroxide is?
A gas.
It's a base, actually. Good try, though. It's a base. So this reaction is an acid-base neutralization reaction, which we had in a previous lesson. So a salt is formed, sodium chloride salt is formed, and water. But do you notice if any of the oxidation states change in the elements? Katie?
They don't.
They don't change, so we would say that this is
Not a reaction.
not a redox reaction, okay? Okay, so this is not redox, there's no transfer of electrons, and this is an acid-base neutralization reaction, and a salt and water is formed. Okay, so a quick review of what we've talked about today before I give you guys your exit ticket. So energy transfer, redox is energy transfer between substances through the transfer of, Katie?
Electrons.
Electrons, right. We must have that electron transfer for it to be redox. So substances in a reaction must lose or gain electrons for the reactions to be considered redox. So we determine the gain or loss of electrons by examining what? Jeremy? Right, oxidation states. We have to examine the oxidation states of each element in the reaction. We need to examine the reactants and then the products to see if the oxidation states change, and if they do, yes, there was a redox reaction. So not all redox reactions involve what? Katie?
Oxygen or hydrogen.
Oxygen or hydrogen, right. So what is another type of redox reaction that we talked about? The transfer of electrons between two. So some do involve oxygen or hydrogen, but what are the ones that don't? Katie?
The ones between metals.
Yes, the ones between two metals, such as in the battery or galvanic cell. Good. Okay. So what do we need to see in a chemical reaction to know that the reaction is redox? Katie?
A transfer of electrons.
Good. Transfer of electrons. So explain why the presence of an oxygen atom in an equation does not always mean that the reaction is redox. So a lot of redox have oxygen atoms, okay? But why, explain why it's not required. Katie?
Because if it doesn't transfer to the other substance, it's not a redox reaction.
It
If there's
doesn't
no
transfer.
Electrons.
Right, very good, well said, yes. So if it doesn't transfer electrons to the other substance, then it's not a redox equation, and oxygen can be in a reaction and not transfer electrons. So explain how rust is a product of a redox reaction. What happens in that process? Katie?
It's the rust comes from the oxidation of iron.
Good, yes. The rust is a byproduct of the oxidation of the iron. Good. Okay. All right, so the next thing I would like to see where you're at by giving you a couple of exit ticket questions. But before we do that, let me explain the procedures once I have passed you through your exit ticket, okay? So you're going to be doing a research assessment, a little research activity as your summative assessment. So what you're going to do is you're going to be doing some research on the tablets, so you need to make sure that you are following our safety guidelines for using electronic devices. You're going to find an oxidation reduction reaction in a living system. You need to write the equation, write the proper equation, make sure it's balanced. And you're going to draw a diagram that's descriptive of what happens in the reaction. Okay? So we went over a few examples in the PowerPoint, or some of living and some of non-living systems. So the next thing you're going to do for number 2 is you're going to write an oxidation reduction reaction from a non-living system. Okay, so you're going to research, find one, write the proper equation out, balanced and everything, and draw another diagram that is descriptive of what happens in that reaction. I'm leaving you space for the to write the reaction. I'm leaving you space for your diagram. The more colorful, the better. And I'm leaving a space for you to write your references. I want you to use at least 2 references. I have listed suggested references. You do not have to use them, but they're a place to start at the top of this form, okay? And I will also hand you the rubric of what I expect for this research, okay? So this is up to 20 points for your assessment. This will serve as your summative assessment for this lesson. So make sure you look over the rubric really well. Okay, so I'm about to put up, so after you're done with your exit ticket, you're going to place it up here on the spectrum. Okay? So I want to know how well you understand this lesson. If you put the sticky note over here, I get this. I don't quite understand, okay? And then somewhere in the middle, okay? So place it somewhere on this spectrum about your understanding of this lesson. So I'm going to give you each a sticky note to write your answers on for the exit ticket. Okay, there's 2 questions. So hand those out for you. Okay, and here is your exit ticket problems. So go ahead and start those. So this
Redox reaction or not?
So with your exit ticket problems, you're going to state whether it's a redox reaction, and if so, is it in a living or non-living system, okay? So go ahead. Yes.
If it's not a redox reaction, do I
Just
still
write
have
no redox? Yeah. You don't have to state whether it's living or non-living. Okay. All right, Katie, good job. You got them right. I'm going to get you started with your tablet and your research guide. Please, if you're getting your research guide and your electronic device, please raise your hand if you have any questions. I'll be glad to come by and answer them for you, okay? All right, let's get started, and whatever is not finished in class can be done as homework and turned in tomorrow. Okay, great job today.